Hello, geometry students. Welcome to lesson 1-3 on the midpoint and distance formulas. We are going to go through the examples of this section and then we'll do the try-its in class. So your notes will have both examples, so we'll be skipping some pages as we go. So the midpoint of a segment, it's the point that divides the segment into two congruent segments. So think of it as an average of the coordinates. So we're going to add up the x coordinates, divide by 2, and then we're going to add up the y coordinates and divide by 2. So in this example 1, we're given coordinates for A and B. So I'm going to take the x coordinates, so -3 plus 4. I'm going to divide by 2. And then 2 plus -2 and divide by 2. And that's just going to give me 0. And here I get 1 over 2. So the midpoint of the segment AB is 1/2, 0. Okay, we'll skip over these try-its. And then example 2, here we're taking a partition of a segment. So the question is, what are the coordinates of the point that is 3/5 of the way from A to B? So when we're doing midpoint, it's half the way, right? So this is different. We can't just add them up and divide by 2. What we're going to do is find 3/5 of the horizontal and vertical change from A to B. So the horizontal change, we're taking 13 minus 3, and then we're taking 3/5 of that, which gives us 6. For the vertical change, now we're looking at the y coordinates. So it's 11 minus -4, and then we're taking 3/5 of that. 3/5 of 15 gives us 9. Our next step is to add the horizontal change to the x coordinate and the vertical change to the y coordinate of the starting point, which is point A. So we're going to add the 6 onto the 3 of coordinate A, and we're going to add the 9 onto the -4 of coordinate A. Of point A, sorry. So once we do that, the coordinates of the points that are 3/5 of the way from A to B is the point 9,5. So here's a diagram that sort of demonstrates what we did. So again, we took 3/5 of the distance, the horizontal distance, which again is the difference of your x's, and 3/5 of the vertical distance, which is the difference of your y coordinates. Okay, calculate those two values and then add those values accordingly onto the x and y coordinates. We'll save the try-its for class. In example 3, we're asked, how can you find the distance between 2 points, P and Q, where P's coordinates are x1, y1, and Q has the coordinates x2, y2. Okay, so what we can do is plot the points. Okay, D is the segment between the points, and then we can set up a right triangle. We can get the lengths of the triangle by taking the difference of the coordinates. So in this case, we're taking x2 from point P and subtracting x1 from point P. We can get the vertical length by taking the difference of the y coordinates. So y2 minus y1. As a precaution, we take the absolute value because these are lengths, so we always want the lengths to be a positive value. So the absolute value of those differences would give us the lengths of the triangle, and then we could set up Pythagorean theorem. If you remember from Pythagorean theorem, it's a squared plus b squared is equal to c squared. And then I'm going to do a substitution Remember, we can call either length A or B. So if I call the x values the length of A, I have x2 minus x1, and I'm taking the absolute value of that, and then I'm going to square it. And then for B, I'm going to replace B with the difference of the y coordinates. So I have the absolute value of y2 minus y1, and I'm going to square that. C, remember, is always the hypotenuse, so that for us is D, so that's D squared. And then to solve for D, I undo squaring by square rooting. So D is equal to the square root of the absolute value of x sub 2 minus x sub 1 squared plus the absolute value of y sub 2 minus y sub 1 squared. Now, here in this triad, I am going to go through this one because it's directly related to that. It says that Tavon claims that D can also equal this. Okay, that it can be used to find the distance, just like the formula we set up. Is he correct? Well, yes, he is, right? Whether if you look at the difference here, we started with x sub 2 and subtracted x sub 1. Because we're squaring, we no longer need that absolute value, because what happens when we square a number? Well, whether if it's positive or negative, we always get a positive result. So that's one thing. The other thing, does it matter if I'm taking the difference? Does it matter if I do x sub 2 minus x sub 1, or if I do x sub 1 minus x sub 2? It doesn't, right? Because whether if I'm taking absolute value or if I'm squaring, either way I end up with a positive result. So the takeaway from this is that you can subtract your coordinates in either order, but you must stay consistent. Meaning, if I start with the point x sub 1, if I start with the point that has x sub 1, then I need to start with the same point and use y sub 1 first when I do the difference in the vertical direction. Same thing here. If I choose to start with the coordinate that contains the x sub 2, then when I do my vertical change, I need to start with y sub 2. That's the key thing. So the distance between 2 points is this formula here. Very important formula, very useful. We will use midpoint and distance throughout our course. Okay, our next example, we have a pitcher that throws a ball to a batter who hits the ball to the shortstop. So let me get my segment maker. Okay, so the pitcher throws the ball to the batter, and then they hit the ball and it goes to the shortstop. So if the ball travels in a straight line between each, what is the total distance traveled by the ball? And then we're asked to round to the nearest tenth. So let's set up our distance formula. First we'll call this d sub 1, and we'll call this d sub 2. So for d sub 1, for the pitcher, I have the coordinates 5, 5. And the batter is conveniently at 0, 0. So when I take the difference, I get 5 squared plus 5 squared, which is the square root of 25 plus 25, or root 50. For d sub 2, I'm now going from batter to shortstop, or shortstop to batter, depending on how you're looking at it. For the shortstop, we have the coordinates 5, 10. So that's the square root of Again, the batter's at 0, 0, so it ends up being 10 squared plus 5 squared, which gives us the square root of 125. Now, since we're rounding to the 10th, I don't need to do any simplification of my radicals. I'm just going to take those roots on my calculator. The square root of 50, I'm getting approximately 7.07, and then a 1. And for 125, I'm getting approximately 11.18. So when I add those together, I'm getting, okay, so the sum of these two, I'm getting 18.25. So if I round to the nearest 10th, since the 2 is followed by a 5, I would round that up to 18.3 feet. Let's check on that. Okay. Oh, this is important. I forgot about our scale here. 1 unit is about 9 feet. So we need one last step here. Multiply by 9. Let me take out my units here. Always important to read your scales, as you can see. So this is actually just units for now. So times the 9 feet, and then that gives us the 164.7 feet. So that would be the total distance that the ball travels from pitcher to batter to shortstop. Okay, so that concludes this lesson. As I said, we'll complete the try-its in class. Okay, I hope you enjoyed the lesson and have a good day.